Everyone, Mr. Fritz here. We're going to talk about constant velocity problems. And let's begin by taking a look at these points OA. So I've got some object. It begins at point A. I want to know what its position vector is. Remember, a position vector is from the origin O to A. So the position is at A, but the position vector is from O to A. So go ahead and draw that in. It should look something like this. And let's just call it vector A for the sake of argument. The next thing I want you to try to do is I want you to think about this object at point A is moving at a constant velocity b. So every second or every interval of time we're moving b units away, or we're moving a vector b away from this point until we hit point R. So what vector would describe this path from A to R? Go ahead and draw that in and see if you match up with what I get. I get this right here. This is AR. Here's my next question. What is the resultant vector? If I move in this OA path and then AR path, draw in the resultant R. It should look something like this. I'm going from O to R, and that's equal to the sum of this vector plus this vector. And the object really will continue to move. It's moving in this velocity, and we can imagine this being a boat or a plane or something like that. We are continuing to move in this constant velocity in this direction. So really R is going to keep changing. And you can maybe even see that this resultant is going to continue to become this longer and longer and longer in different direction R as this vector or as this particle keeps moving on and on and on. This resultant is going to kind of stretch and move and move and move and move and move. The resultant is going to continue to change, as I said, but in general, if I wanted to find this vector, this resultant vector, it's going to be whatever OA is plus whatever AR is. And this R is going to continue to move as time goes on. Now here's the kicker. AR is equal to T times vector B. I want to let that sink in. This AR vector I can figure out by figuring out how many B's I can fit inside of this AR. Or thinking about the number of seconds, let's say we're talking about time is in seconds. For each second, I'm moving another B in this direction. So this AR will be described as really how many seconds have passed times the number of B vectors being used. So if there were 3 seconds, then there should be 3 B's inside of this AR vector. And if we know that OA, if we call that vector A, and we know that AR equals the time times vector B, we can conclude that the resultant vector, R, in general, is equal to this A times plus the time passed multiplied by the vector B. This is like the general vector velocity equation. So this is really key. So let's see how we can use this velocity in an example. This is a constant velocity problem. I have an object that's initially at this point, and it moves with a velocity vector of 3i minus j. So I'm looking at this right away, and I'm thinking this is the same thing as 3, negative 1. I want to find the position, not position vector, but the position of the object at any time t. In this case, t is in minutes. I want to do all kinds of stuff here. So let's start off with letter A. And in general, R is going to equal I'm sorry, I want to find the position, not the position vector or anything like that. But let's just write down, in general, this vector R resultant is going to equal A plus T times B. And if I want to find the position, let's think a little bit about what we know about the vector equation given in this example. So this xy position vector should be given by my initial position, and the initial position vector is going to be 5, 10, plus time times my velocity vector, which is 3, negative 1. And if I take this information, kind of crunch it together, I know that my xy position vector is going to be given as 5 plus 3t and 10 minus t. Basically what I just did is I added these two vectors together. So the position point, the point of my position, the coordinate of my position, is going to be, basically the x will be this, 5 plus 3t, and the y will be this, 10 minus t. So this in general is going to give me position at any time t. Notice this is a position, not a position vector. That's why this is written as a coordinate, not as a vector. So that's A. Let's talk about B. I want to find the position at t equals 3. Well, this is pretty straightforward since I just spent all that work finding the position at any time. So I'm going to take point P will be at 5 plus 3 times the time is 3, comma 10 minus 3. And so the position will be at, what is that, 14, 7. All right, and then finally, the last piece of this is to, let's do another color here. The next piece is to find the time when the object is due east of the origin. So let's think a little bit about this for a second. Kind of graphically what's going on, I've got this object up here at 5:10, about here, and it's moving to the right and down. So it's kind of moving in this direction. Eventually, it's going to cross the x-axis. This is east of the origin. Here's my origin 0, 0, and due east would be right here. So really another way of asking this question is when is the y equal to 0? Because due east would be when my y equals 0. So in order to find that, I just have to look at my y values. And we found the parametric equation y of t is equal to 10 minus t. So I want to know when this equals 0. 0 equals 10 minus t. Do a little bit of algebra. And I find that t equals 10 minutes. That's how long it'll take for me to be due east of this point right here. So why don't you try this example? It's a whole lot like the last one. Pause the video, give this one a shot. All right, so here is the solution to this problem. Constant velocity, pretty straightforward as long as you can handle the vector equations.